Now, we need to be able to go from sets to logic and back. Okay, that's going to be an important skill. So let's try a few different observations, right? So here is a statement: A belongs to 1, 2, 5, right? This is the set 1, 2, 5. Okay, well, that statement is actually equivalent to this logical expression: A is equal to 1, or A is equal to 2, or A is equal to 5. Okay, I can do that whenever you give me a set by listing a finite number of elements and saying these are the elements in this set. Okay, so A belongs to that. Remember, A belongs to a set is a predicate. Okay, so that predicate is actually equivalent to this logical statement: A is equal to 1, or A is equal to 2, or A is equal to 5, right? You could imagine that this could be step 1 in a proof, and this is step 2 in a proof. Okay, and this the explication might simply be definition of belongs to. Okay, because that's what we mean by belongs. So it means that A is one of the elements in it. Okay, now let's look at this other, which is a slightly more interesting set because it's defined using a rule, right? And here what we have is that here's the rule, right? And A belongs to that set. Well, what that means is that A must satisfy this rule. Otherwise, it wouldn't be in this set. Okay, so here it is. There exists in K such that A is equal to 7K. And notice that what we've done is we've taken the X, which is here, right? Okay, and then we've put A in there because A belongs to. A is one of the X's such that there exists a K such that X is equal to 7K, right? That's the way I read that, okay? So A has the property that defines the set, okay? Now, the most complicated one looks like this. And that's like A belongs to 1 over P where P is prime. And that's because we have a pattern, not just a rule, okay? So here is the equivalent logical expression, right? And the equivalent logical expression kind of has two parts. Here's the first part. And this part says P satisfies the pattern, okay? Notice that that's not the same, okay, as A satisfies the pattern. It's P that satisfies the pattern. There is some P that satisfies the pattern, or I'm sorry, the rule, okay? And then A is equal to 1 over P, and so A comes from the pattern. Okay? So it's like a two-step statement. The first statement is, oh, I found an element that satisfies the rule, right? That's P. P is prime, right? Now that I've found one of the elements that satisfies the rule, it turns out that A can be derived from that element by using the pattern that we're interested in, right? So those are the kind of the statements that we're making. I really want you to understand how to translate from A belongs to some set into a logical property of A, because we're going to use that in all our proofs, right? We'll say, oh, let's start with A belongs to S. Well, that must mean that, and here's step 2 in the proof, right? And then we'll go from there, now using everything that we know about logic and quantifiers and that sort of thing. Okay, so I want to give you a really strong caveat here. This is an important warning because this is something that I saw a lot of students in the past kind of getting confused on. Okay, so let's look at this set, right? Let's scratch that. Let's just look at the set. Okay, so the set of all X such that X is equal to 7K. That's the way that I read that set. Okay, this is the set that contains all of the X's that have this property that X is equal to 7K. Okay, now the problem is that this says of all. Okay, and so it's natural to get confused with the way in English that we talk about a quantifier. For all X, this is true. Okay, but actually there's no quantifier here. When I simply write this, what I'm describing is a collection of elements. Okay, if I say for all X something, then I'm talking about a proposition which is either true or false, right? Proposition is actually the wrong word to use in this context. What I really mean is like a predicate, okay? But propositions are the things that are always either true or false. That's why I use that word. Whereas predicates, it depends on whether I say for all or there exists, okay? Now, I've seen a lot of students kind of try to do this in a proof, okay? So they start by writing some kind of a set. The set of all X such that there exists a K at X equal to 7K. That's a very odd place to start, okay? That's like starting with the number 3, because this is a collection of objects, right? That is not a statement that is either true or false. It's just a collection of objects. So when we're doing proofs, we're actually talking about statements that are either true or false. That's what we're proving. So that's kind of an odd thing to start with, right? Because we're starting with like a number. We're starting with 27 and then saying, and that's true. No, it can't possibly be true, right? It's just a number. So that's kind of an odd start. But then comes kind of the killer move, which is this. And so what we have here is a collection, right? And what we have here is a statement, which could be true or it could be false, but it's a statement. So how can these things be equal to each other, right? True or false is not the same as the collection of the numbers 1, 2, and 3. No, it can't be, right? They're not even the same kinds of things. It's a little bit like when you have code and you write if, and you write a string like hello world is equal to the number 12. It can't ever be true, right? So hopefully your favorite programming language actually gives you a syntax error at that point. It says, I know you don't mean this, okay? But that's what you're writing when you do this. So don't do that, okay? Sets are collections of things. Statements are true or false. Don't confuse the two. Okay, enough of that. So, oops. Let's look at some, well, this is kind of really just an aside. I mean, we talked about sets, okay? And they're not the most common data types that you might use in a program, but they're actually there quite a bit. So for example, this here is Java, okay? And Java has what's known as the Java util collections package that has a lot of really useful things like vectors and lists and sets and hash tables, for example, right? I mean, it's trees, and it's got lots of really, really useful things. And here is a hash set. So this is a specific kind of set, okay? So we have here a set of strings. And it's a set of strings, so I can add strings to it, right? This is a kind of an empty set when I create it, right? This generates an empty set of strings. And now I can add Fred, I add Sally, and so now my set has 2 strings in it, Fred and Sally, okay? This is another way to construct a set that contains Fred and Sally. This is just, that actually looks a lot like mathematical notation. It's just a brace, Fred, comma, Sally, and that's what set 1 is. This is Python, okay? And Python actually has sets. It's got 2 syntaxes for sets. Here's kind of my preferred method. Here's another one where we use a list and then convert it to a set using the set constructor, okay? There's other languages that don't actually have sets explicitly, and instead what they do is they reuse some other kind of types. So for example, you might use a dictionary. It's also called a map or a hash, and that's just a collection of key value pairs, right? So Java util map is an example of this kind of collection, right? In Python, this syntax here is also Python, okay? Then you can have a list of elements. This is a list that has the elements Fred and Sally. This is a map, okay? So right here we have a map. Python actually calls it a dictionary. And this thing is just a list, which in Java you might call, actually we do have lists. We have array lists, right? So yeah, that's standard notation for that. And so now what you can do is if it's a list, then you can just go through the list and see if the member you want is in there, right? If it's a dictionary, then you can actually just ask for its value, right? What is the value of sdict Fred? And it'll either give you an error, meaning I don't have a value, or it'll actually give you the number 1. So that's how you know if Fred is in that set, okay? So, okay. I can't help but mention a really kind of a super cool aspect of Python, okay? So I say some super cool languages, but really what I'm talking about here is Python, which is a super cool language. And this is called a comprehension, okay? And actually in sets they're called comprehensions. So that is a comprehension, okay? And what makes it a comprehension is this for p in that. So this is actually equal to the set of 1 over p, right? Such that p is in this range, which means p is in 2 up to 100, okay? I could write it like that, or I could simply write 2 is less than or equal to p, and p is less than or equal to 100. The 101 is because it goes one past, just stupid notation, okay? And p is a prime. Okay. Now this is very similar to what we said before, the set of all 1 over p such that p is a prime. The only thing extra is this part here, and this keeps a finite set. Okay. If you don't have that, then it's an infinite set that contains 1 over any prime. And in programming, we don't mean that, right? We just need to stick to kind of finite data structures. So this is actually precisely a set comprehension or a list comprehension. The first one here is a list. This one here is a set. Okay, but it's a way of specifying a set using a property, which is very, very nice. Okay.